Okay. So again, we're going to start. With the knowledge that we've already developed the element stiffness matrix for an arbitrary oriented frame element. Okay. So we're going to consider this element right here. We're going to call that element 1. Okay. So what I'm going to call KE1, that'll be the element stiffness matrix for this element. Okay. That's equal to KEG, because that's what I called that, remember. Evaluated at alpha equals minus pi over 2. That's minus 90 degrees. And I told you why the negative sign's there. And then the length of it, we're going to go ahead and put that in there as well, is 144 inches. Okay. All right, so there's our element stiffness matrix for the first element, and the rotation has been applied. So it's actually in the global coordinate system at this point. Okay. Now we need to calculate what the element force vector is due to distributed loads. So we'll call that FE1. All right, that's going to be, we've done this many times, 0 to L. It's going to be F of X, but in this case, I wrote down what it is. It's P over 72, okay, times in beam. All right, so we only need to multiply by the shape function of the beam, because the bar shape functions don't support transverse deflection. So we'll have that there, X, where I goes from 1 to 6. Okay, and if you remember when I defined those shape functions, so there's the shape function for the bar. There's zeros in as placeholders at the locations where the beam would be. The bar, I'm sorry. So where the axial degrees of freedom are, okay? And that's reflected here, that these zeros appear, okay? But again, this was formulated in the local coordinate system, which has X going up and W going this way, right? We need to rotate that into the global coordinate system. So the way we do that is we just say, we use our transformation matrix that we defined last time. Okay, and then we'll go ahead and plug some numbers in here as well. The transformation matrix is a function of alpha, so we need to say alpha is minus 90 degrees, and L is going to be 144. If we do that, we get this. Okay. So now this is the element force vector in the global coordinate system. So if you notice now, I haven't applied this load. I've only applied the distributed load, and therefore there's no force components in the the up and down direction. There's zero, because everything is acting left and right. All right, so that's for the first element. Now we can do the same thing for the second element. The stiffness matrix for the second element, which I'll call KE2, is KEG evaluated at alpha equals minus arc tangent 3 over 4. And L this time is going to be the square root of 108 squared plus 144 squared. All right. Everybody understand why I did that? So I'm trying to find the length of this element. So it's 144 squared plus 108 squared. Take the square root of it. The hypotenuse of that triangle. So there's the element stiffness matrix. So you can already see, you know, how ugly it gets. So now for the element force matrix, we have to consider that force that's being applied right here, okay? And this is where we break down the components. So here's where we use the shape functions to distribute it to the nodes, okay? Because this doesn't apply, you can only apply point forces at nodes, okay? So we need to use the shape functions to distribute it to the nodes, okay? So what we'll do is first we'll only consider the axial component, okay? So for the axial component, we have Fe2 equals table, and then what we're going to do is we're going to say 4p times the arc tangent of 3/4. Okay, but what we actually want, because that represents alpha, okay, but what we actually want, as I wrote down over there, is for the axial component is the sine of alpha, right? I didn't mean to write over that. Okay, and we're going to multiply that. The axial component is where only contribution comes from the so-called bar shape function, right? All right. We need to evaluate it at the location that that point load was applied, which is L/2. Okay. And then we can also go ahead and if we like, we can plug in values for L. Or we don't need to, actually. That's right. Okay. So that's the contribution from the axial component. Now we need to add in contribution from the transverse component and any moments that are applied. So now we have 4p times the cosine, arc tangent 3/4. Okay. Sorry, this should have been switched to beam. All right. So you see that force, because it's applied at an angle, once it's distributed to the nodes, you end up with forces in both directions and moments because of that. All right, so then the last thing we want to do, this is still all in the element coordinate system. We want to change that to the global coordinate system. So our last thing would be to transform it and we need to plug in our angle. And we can plug in the value of L there.